So let me share the screen also. Is the screen visible to you?
Yes, sir.
Right. So we discussed about a vector space, okay, or a field F. This field can be real or complex, on which you can define one more operation called inner product. Okay, this is denoted with the inner product, satisfying certain properties, linearity and non-negativity and symmetry in the case of real inner product space. Okay, if this field is real numbers, set of real numbers, the set vector space together with the inner product is called Euclidean space. If the field is a set of complex numbers, I said the vector space which is also associated with this inner product is called Euclidean space. And I said we are confining our discussion to the Euclidean spaces, where you have a vector space together with an inner product space with reference to the set of real numbers. And after that, we discussed about norm. Okay. So norm we define as a square root of the inner product between u and u, or you can say norm u whole square equal to inner product of u comma u. Okay, basically this is a thing to say magnitude I said. And I also we talked about inner product of two vectors through dot product. If you are having u equal to u1, u2 and so on un, and v equal to v1, v2 and so on vn, inner product of u comma v can be defined through dot product as u dot v, which is u1 v1 plus u2 v2 plus and so on un vn I said. Okay, so this is one way of defining the inner product. Okay, and this kind of inner product for vectors of 2 dimensions, vectors of 3 dimensions, and this is a generalization to vectors of n dimensions. And after that we talked about orthogonality. Whenever the inner product is 0, we said that u is said to be orthogonal to v, and the set of all orthogonal vectors is said to be an orthogonal set. And I also said orthogonal set is basically linearly independent set. Okay. And that orthogonal set becomes orthonormal if norm of each vector is a unit vector 1. That means each vector is a unit vector. Okay, unit vector is nothing but u divided by its norm. Okay, so the set of unit vectors which are orthogonal to each other is said to be orthonormal set of vectors. And the question is, if for a vector space, if there is a basis b, then how to construct a orthonormal basis? That we did by Gram-Smith orthogonalization process. By Gram-Smith orthogonalization process, we formed the orthogonal set. Okay, so if this basis is containing n elements v1, v2 and so on vn, which are linearly independent, not necessarily orthogonal to each other. Okay, then we want to find out an orthogonal set. Orthogonal set as w1, w2 and so on wn. Okay, using these basis vector. And if this is an orthogonal set, we know orthogonal set of vectors are linearly independent. Any linearly independent set of vectors containing n elements is going to form a basis. Therefore this set is actually nothing but a basis. Okay, so for a given basis of a vector space, how to find out its orthogonal basis? Okay, he is given by a procedure. Okay, what is that procedure? You take w1 as v1 and w2 as, what is w2? v2 minus, okay, v2 into v2 inner product with w1 by norm of w1 into norm of input of w1 comma w1 into v1. Am I right? Let us cross check once. Okay, so v2 w2 equal to v2 minus inner product of v2 with w1 by w1 into w1. Okay, so this is w1. Okay, so this is w1. So what is and what is the inner product of w1 comma w1? Inner product of w1 comma w1 is nothing but, you can see inner product of u comma u. Inner product of u comma u is nothing but norm u whole square. What is norm u whole square? With respect to this sense, under root of u1 square plus u2 square plus and so on plus un square. Because if this is u and if this is u, u dot u is u1 into u1 plus u2 into u2 plus and so on un into un. That means u1 square plus u2 square plus and so on un square. So this is whole square. Okay. Whole square, or these two gets cancelled. So simply you will get a u1 square plus u2 square plus and so on un square. Sum of squares of the compounds. So this is basically v2 minus inner product of v2 with w1. Okay, inner product you can call it as dot product only, because we are going to see dot product only. Okay, so you can put comma here, and this w1 comma w1 is nothing norm w1 whole square into w1. Similarly, how do you find out w3? w3 is nothing but v3 minus, you take the third element, minus inner product of v3 with w1 divided by norm w1 whole square into w1 minus inner product of v3 with w2. w2 is this one. Okay, divided by norm w2 whole square into w2. And this procedure can be extended to any number of elements. Okay, so if you have 3 elements, you can write the formula up to this. If you have 4 elements in the basis, you can write the formula up to w4 and so on. So basically, okay, norm w1 whole square. Okay, norm w1 whole square. Norm w1 whole square is nothing but magnitude, square of the magnitude. Okay, and this is nothing but dot product. And so that can be done very easily by substituting those things in this formula. So what I would like to highlight in this point is, suppose you have let us say 1 2 3, let us say 2 3 6. These two are linearly independent. Do you agree? 1 2 3 2 3 6, because one vector is not a multiple of another vector. If I want to get 2, I should multiply with the 2. 2 into 1 is 2, but 2 into 4 is 2 into 2 is 4. It is not 6. So you cannot express this vector as a constant multiple of this vector. So these two are linearly independent. These two are linearly independent. Okay. Okay. So if you want to get a vector, okay, if you want to get a vector which is orthogonal to these two, if you want to get a vector which is orthogonal to these two vectors, how do you get? For up to 3 dimensionals, it is very easy. Okay, because you can generalize. You have a vector this, you have a vector this, call this as u vector, call this as v vector. You have a vector u, you have a vector v. If you want to find out a vector which is orthogonal to u and v, can you tell me with your previous knowledge, how can you get this vector which is orthogonal to these two vectors? Any idea? Only with this knowledge. Let us suppose that you didn't attend any linear algebra course. You know only up to first year knowledge. For a given vectors, can anyone tell?
Dot product of they are zero, sir.
See, I want a vector which is orthogonal to these two. Okay, that is there. See, one point is I want W like X, Y, Z. Okay, we discussed this previously. I want W W must be perpendicular to U. That means what? W dot product V. Sorry, W dot product U must be 0. That means X plus 2Y plus 3Z equal to 0. You are right. I agree. And another one is W also must be perpendicular to V. That means W must be perpendicular to V. That means what? The W dot product with V must be 0. That means 2x plus 2x plus 3y plus 6z equal to 0. And this is a homogeneous system. You solve that homogeneous system for x, y, z for different values of k. You will get different vectors which are orthogonal to both u and v, I said. That is there. This is a general procedure which is applicable to not only 3 components, it is applicable to any number of components. You can, whether it is having 4 components, 5 components, 7 components. This is a general method. I agree that we have seen. But if it is having only 3 components, is there any other way that you know to find out an orthogonal vector? If it is a 3-dimensional vector, what is the other way of finding? Do you know? At least one vector you tell me. From physics, do you know any property? In physics, you learnt dot product. Anything else you learnt?
Cross product.
So what is the geometrical meaning of cross product of u and v?
Perpendicular to both u and v.
That is what I was asking, no? So cross product of u and v is a vector which is normal to the plane containing u and v, right? Right or wrong?
Yes, sir.
So if you are having only 3 components, you just take the cross product. That also will work. But cross product we don't know for 4-dimensional, 5-dimensional, 6 dimensions. That's why we need to employ this procedure. So that if you are having 3 vectors, okay, and having 4 components each, then you employ this condition, okay, so that you will get a system of linear equations for any number of components. So this is a general procedure. If it is having only 3 components, you can employ this procedure also in case if you want an orthogonal vector immediately. Is this point understood you?
Yes, sir.
Right. Now I will quickly recall eigenvalues and eigenvectors, and then go to diagonalization. From diagonalization, we will see what is a singular value decomposition. Okay. So can anyone tell what do you mean by eigenvalue and eigenvector? Can you please quickly recollect? A is a matrix. What kind of matrix it is? Is this any matrix of any order? Any particular assumption is there? For eigenvalues, eigenvectors, what kind of matrix we are supposing? For a system of linear equations, Ax equal to b, what kind of matrix we supposed? A is an m by n matrix, right? Where number of equations may be equal to number of variables. You have seen number of equations more than number of variables. You also have seen number of equations less than number of variables. Any case is possible in case of system of linear equations. But what kind of matrix we considered in eigenvalues and eigenvectors? Do you remember? Matrix of order n. Eigenvalues and eigenvectors exist basically for matrices of order n. So this is m by n, this is n by 1. Product is n by 1. Okay, so what do you mean by eigenvector? Eigenvector is a non-zero vector. Okay, so you multiply A with X, output is some Y of order n by 1. If you can express this Y as a scalar multiple of the original vector X, we don't know whether that is possible or not every time. But if that is possible, if you can express the output vector as a multiple of the same vector, then we say this vector is eigenvector, and the corresponding scalar is called eigenvalue. Okay, basically eigenvectors are non-zero vectors satisfying this condition. Okay, ax equal to lambda x. Okay, if you cannot write this output as a multiple of the same original vector, then this cannot be called as a eigenvector. So it is obvious that not every vector is an eigenvector of a given matrix. Okay, so we want to find out all the vectors, all the eigenvectors corresponding to the matrix. For that, what is the procedure? You know, you will be solving the characteristic equation, right? What is characteristic equation? Determinant of a minus lambda equal to 0. And when you solve the characteristic equation, if it is of order n, you will get n eigenvalues. Okay, lambda 1, lambda 2, lambda 3, and so on, lambda n. And for each of the eigenvalue, what you have to do? For each of the distinct eigenvalue, you have to solve a minus lambda k. Let us say lambda k is a particular eigenvalue. Okay. So then for each of the distinct eigenvalue lambda k, you solve the system a minus lambda k into I of x equal to 0. This is a homogeneous system. All non-zero solutions, okay, all non-zero solutions are called eigenvectors corresponding to the eigenvalue lambda, Okay, and these eigenvalues may be real, these eigenvalues may be complex, all the eigenvalues may be distinct, some of the eigenvalues may be same. So all cases are there. Okay, and so that is the procedure. That is about finding eigenvalues and eigenvectors. And there are several properties listed on eigenvalues and eigenvectors. Some of the important properties are some of the eigenvalues must be equal to trace of the matrix. Product of eigenvalues is equal to what? Do you remember? Product of eigenvalues is equal to determinant of A. Do you remember or not?
Yes, sir.
Trace of A equal to lambda 1 plus lambda 2 plus and so on. Okay, from this you also got various relations like if any one of the eigenvalues is 0, product is 0, that means A is going to be singular. If all the eigenvalues are non-zero, then A is non-singular, right? So whenever you see a 0 as an eigenvalue, that means the matrix is going to be a singular matrix. Okay, otherwise none of the vectors are none of the values are zero eigenvalues. Okay, so so there is one more thing, you know. Suppose A is a 3 by 3 matrix. Eigenvalues can be 3, 4, 6. Eigenvalues can be -3, 4, 0. Or eigenvalues can be 2, 0, 0. Okay, you know what are these suggesting? You know how to find out rank of a matrix, right? How do you find out rank of a matrix? So far, you convert this into echelon form and identify the number of non-zero rows. That is going to be the rank of the matrix. Am I right?
Yes, sir.
But you can find out rank of the matrix through eigenvalues also. You count the number of non-zero eigenvalues. That is going to be the rank of the matrix. You can verify later. In this case, if the eigenvalues are, so order is 3, all the 3 are non-zero, then rank is going to be 3. Okay, order is 3, but there are only 2 non-zero eigenvalues. One is 0, then rank is going to be 2. Order is 3, but only one non-zero eigenvalue. That means rank is going to be 1. So rank of A can also be equal to the number of non-zero eigenvalues, the number of non-zero eigenvalues of a matrix. And this can be classified as a positive definite, semi-positive definite, depending upon all the eigenvalues are positive or some of the eigenvalues are only positive. In this case, this is called positive definite. In this case, this is called semi-positive definite. And instead of this, if you are having -2, 0, 0, this is called semi-negative definite. If you are getting -3, -4, -6, this is called negative definite. And if you see some eigenvalues as positive, some eigenvalues are negative, that is called indefinite. This is called indefinite. Okay, and this is related to some quadratic forms. That topic is removed from your syllabus, so you don't know about this. Okay, so this positive definiteness of a matrix is also very important concept. Okay, that can be observed through these eigenvalues. All eigenvalues are positive, positive definite. All eigenvalues are negative, negative definite. Some eigenvalues are positive, remaining are 0, semi-positive. Similarly, semi-negative. Both are present, indefinite. That's it. Okay, so that's the case. Next, what I want to talk about is diagonalization. What is diagonalization? Cayley-Hamilton theorem is anyway you know. What is diagonalization says? Suppose if you have a matrix, if obviously all matrices are of order n in eigenvalues and eigenvectors. Suppose you have a matrix A. Okay, suppose you have a matrix A. Okay, and if you can find out, okay, if there exist P, okay, such that B equal to P inverse AP, such that B equal to P inverse AP. Then we say these two are similar matrices. Then we say A is similar to B. Similarity. A and B are said to be similar matrices. Okay. So this kind of thing we have seen earlier in change of basis. Okay, I told you to verify one property. Okay, matrix of the transformation related to one basis can be expressed as like this P inverse matrix of the transformation with respect to the original basis into transformation matrix. That means matrix of the transformations with respect to different bases are actually similar matrices. Okay, and if this B is turning out to be a diagonal matrix, if this B is turning out to be diagonal matrix, okay, that means P inverse AP for some P, then that means to say that A is similar to a diagonal matrix. Whenever A is similar to a diagonal matrix, okay, then we say A is diagonalizable. A is diagonalizable. In that case, D is called spectral matrix. In that case, D is called spectral matrix, and P is called model matrix. P is called model matrix. Okay. So what is the procedure to find out model? What is the procedure to diagonalize a matrix? Okay. First of all, we don't know whether a given matrix is going to be diagonalizable or not, because it says if there exists a matrix P. If there is no, if there does not exist any such matrix, then matrix cannot be diagonalizable. So that means to say that not every matrix is diagonalizable. Only few matrices are diagonalizable. So how do we identify whether a matrix is diagonalizable or not? Means necessary and sufficient condition is algebraic multiplicity must be equal to the geometric multiplicity. Algebraic multiplicity must be equal to the geometric multiplicity. Okay. What is algebraic multiplicity? What is geometric multiplicity? That can be seen from here. Okay. See, if all the eigenvalues are same, algebraic multiplicity is in multiplicity of the eigenvalue which is occurring as a root. How many times 2 is occurring?
3 times.
So its algebraic multiplicity is 3. Algebraic multiplicity of 2 is 3. That is denoted with t. And corresponding to lambda equal to 2, you will be finding the eigenvectors, right? And that eigenvectors may be turning out to be some k1 into 100. K1 into 100 means what is independent eigenvector? 100. So this is the number of linearly independent vector associated with this eigenvalue. That is called geometric multiplicity of the eigenvalue. So in this case, there is only one independent vector corresponding to 2. Therefore, its geometric multiplicity is 1. It is denoted with S. And the case can be like this. Eigenvalues can be 2 to 8. That means 2 is occurring 2. Therefore, eigenvalue of algebraic multiplicity of 2 is 2. 8 is occurring only one time. Therefore, algebraic multiplicity of 8 is 1. Corresponding to 2, you can have 2 linearly independent eigenvectors. Then this 2 is called geometric multiplicity of 2. Okay. And if it is only 1, if you are getting only 1, then geometric multiplicity is going to be 1. Okay. And in this case, only one independent eigenvector. Therefore, GM equal to 1, AM is also equal to 1. Similarly, if all the eigenvalues are distinct, okay, then 0, 3, 15 occurring only one time. Therefore, the algebraic multiplicities are 1, 1, 1 only. Corresponding to each eigenvalue, you will be getting eigenvectors like this. That means geometric multiplicity is also 1. There is a result saying that geometric multiplicity cannot exceed algebraic multiplicity. And that means AM is 1, then GM has to be 1. If AM is 2, GM can be 1 or 2. That means you can have only one independent vector, you can have two independent vectors. Similarly, if AM is 3, GM can be 1 or 2 or 3. Okay. So what is the condition for diagonalization? This must be same. 3 must be equal to 1, 2 must be equal to 2, 1 must be equal to 1, 1 equal to 1. So AM must be equal to GM for each of the eigenvalue. Then only the matrix is going to be diagonalizable. Okay. So in these three matrices, can you identify which matrix is not diagonalizable?
First matrix.
First matrix. Because for the first matrix, AM equal to 3 for eigenvalue 2, GM equal to 1, 3 not equal to 1. Therefore, you cannot diagonalize this matrix. There is no non-singular matrix P such that P inverse A equal to D. This is not diagonalized. Whereas in the remaining cases, that is possible. Okay. So for AM equal to GM case, you count the total number of independent eigenvectors. 2 plus 1 is 3. Because eigenvectors corresponding to distinct eigenvalues are linearly independent. There is a result. These two are linearly independent. These two belonging to distinct eigenvalues. Therefore, these two are linearly independent. These two are corresponding to distinct eigenvalues. Therefore, these two are linearly independent. Any two vectors are mutually independent means all the three vectors are mutually independent, collectively independent. Therefore, you are having 3 independent vectors. So similarly, you are having 3 independent vectors. That means the matrix is going to be diagonalizable only if it is having n linearly independent eigenvectors. If it is having less than n independent eigenvectors, it cannot be diagonalized. Okay. And one of the sufficient condition is if all the eigenvalues are distinct, definitely it is going to be diagonalizable. If some of the eigenvalues are same, it may be diagonalizable, it may not be diagonalizable. Unless you find out the eigenvectors, you cannot come to a conclusion that it is going to be diagonalizable or not. But you can come to the conclusion of diagonalization immediately by looking at this case, because all the eigenvalues are distinct. When all the eigenvalues are distinct, definitely it is going to be diagonalizable. So all the eigenvalues are distinct is only a sufficient condition, but not necessary for a matrix to be diagonalizable. Even some eigenvalues are same, it may be diagonalizable. Some eigenvalues are same, it may not be diagonalizable. Is this concept clear to you? Okay.
Yes, sir.
Now, how to diagonalize a matrix is demonstrated here. I will just quickly show you. So, test whether the following matrix is diagonalizable. If diagonalizable, find the model and spectral matrices. Okay, in this case, the eigenvalues are 2 to 8. I think I recollected the same matrix, 2 to 8. Corresponding to 2, these are the eigenvectors. Corresponding to 8, this is the eigenvector. So, I wrote those things. Okay, so corresponding to 2, when you solve the system of linear equations a minus 2i into x equal to 0, you will get solution of this form k1 into this vector plus k2 into this vector. I am calling this as x1 and x2. So you are getting 2 linearly independent eigenvectors. Corresponding to 8, you are getting one independent eigenvector. So what are the 3 vectors? 3 independent vectors means x1, x2 and x3. And what is your candidate P? You just put these vectors. You put these vectors in columns. You put these vectors in the columns. You will get a matrix, and this is going to be non-singular because these three are linearly independent. Therefore, P is going to be non-singular. When it is non-singular, you can find out P inverse. Okay, so students computed P inverse and told me, I copied that. And if you check P inverse AP, if you compute P inverse AP, it is turning out to be diagonal matrix, whose diagonal elements are nothing but eigenvalues 2 to 8. So if you get 2, 3, 8, that means you did somewhere mistake, because diagonal elements of D must be the eigenvalues of A. Otherwise, it is a mistake. Okay, so and this is not, P is not unique. You can arrange these three vectors in any order that you want. You can write x3, x2, x1. If you write x3, x2, x1, x3 corresponding to 8, therefore the answer is going to be 8 to 2, 2, like that. So how you are arranging the vectors, correspondingly the eigenvalues also will form in that order. Okay, so that means to say that model matrix is not unique. Model matrix is not unique. Okay, so you form the model, you form the matrix by putting these independent eigenvectors as columns, find out P inverse, show that P inverse AP equal to diagonal matrix. Okay, now spectral matrix is nothing but this diagonal matrix. And what is the application of this diagonalization? See, P inverse AP equal to D means what? You multiply both sides with P. Then what do you get? P inverse cancels, AP equal to PD. Or A equal to what? A equal to PD, post multiply both sides with P inverse. PD, P inverse. Okay, PD, P inverse. What is the advantage of this? If you take A square is going to be P D square P inverse. A cube is going to be P D cube P inverse. If you do this simplification, in general, A power M equal to P D power M P inverse. Suppose if I want A power 1000, if you don't know that whether A is diagonalizable or not, if somebody asks you to compute A power 1000, A into A square into A square, A power 4, A power 4 into A power 4, A power 8. So like that, repeatedly you have to multiply, or even if you write the program, that eats a lot of memory, and the computational time is also high, very high. But what is the advantage here? Even A power 1000 is just multiplication of two matrices, P into D power 1000 into P inverse. What is D power 1000? D power 1000 is nothing but diagonal matrix 2 power 1000, 2 power 1000, 8 power 1000. Is it okay? So any integral power can be simplified just with two multiplications. How advantage this is, right? So that is how this decomposition is useful. Okay, so what is this? This is nothing but a kind of decomposition. You are expressing A as a product of matrices P into D into P. So once you have the decomposition, you have several advantages. Okay, you can do many things from this. Do you remember another decomposition that you have learnt in already in LEMC? What kind of decomposition you learnt other than this?
LU decomposition.
LU decomposition, A equal to L into U. You remember? So this so decomposition also a very important problem in linear algebra. How can we decompose a matrix into product of matrices? Okay, each decomposition has a special application. Okay, now this is just a diagonalization. There is one more concept called orthogonal diagonalization. Okay, now we'll come back to this one note. So what is a diagonalization? Means expressing A equal to this. Expressing A equal to PD P inverse. PD P inverse. What is P? P is just a non-singular matrix. Okay. And what do you mean by orthogonal diagonalization? If this non-singular matrix is turning out to be orthogonal matrix. Orthogonal matrix. then A is said to be orthogonally diagonalizable. What is the advantage of orthogonal matrix? What is the definition of orthogonal? You remember? P into P transpose equal to I. Do you remember? A transpose equal to I means A is called orthogonal. Am I right? Do you remember this? Do you agree with this point? Hmm?
Yes, sir.
Okay.
Yes,
If it is an orthogonal matrix, what is inverse of P? For an orthogonal matrix, what is P inverse? P transpose. Do you agree? Whenever A into B equal to I, B is called inverse of A. Okay. So that means what? I can replace this inverse with transpose. What is P? Orthogonal matrix. Okay. Then we say A is said to be orthogonally diagonalizable. Okay. Now the question is, when a matrix is going to be orthogonally diagonalizable, there is a sufficient condition saying that if A is real symmetric matrix, if A is symmetric matrix and A is a real matrix, definitely it is going to be orthogonally diagonalizable. If it is not real symmetric matrix, it may or it may not be orthogonally diagonalizable. Okay. And how do you find out orthogonal matrix? You know, there are two important properties of orthogonal matrix. Okay. I will write one example. Sin theta cos theta minus cos theta sin theta. I'll write okay. So you see this one. What if you verify P into P transpose, you will observe that this is going to be identity matrix. That means it is a orthogonal matrix. What are the additional features you are having? Similarly, I can write one more matrix like minus 1 by root 2, 1 by root 2, okay, 1 by root 2, minus 1 by root 2. This is also an orthogonal matrix. This is also an example of an orthogonal matrix. And one more orthogonal matrix is 1 0 0 1. Okay, so like this, we can write 3 by 3 matrices, 4 by 4 matrices, 5 by 7, 5 by 5 matrices. Now, if you see each column as a vector, what properties these vectors are having? Can you tell me? You call this as U. You call this as V. Then what are U and V? Can you see any relation between U and V? Observe carefully.
Integration.
No. I'm talking about vector. See, I've been whatever I'm talking now, it's all are interconnected. At the starting of the class, what I discussed about orthogonal vectors, right? When do you say two vectors are orthogonal? With the dot product. What is the dot product of these two vectors? 0. Am I right? What is the dot product of these two vectors? 0. u1 u2 v1 v2. U dot v is u1 v1 plus u2 v2. Minus sin theta cos theta plus cos theta sin theta 0. Minus 1 v2 plus 1 v2 0. 0 plus 0 0. Are these two orthogonal?
Yes, sir.
Same is true for 3 by 3 matrix. Same is true for 4 by 4 matrix. Okay. In an orthogonal matrix, any two vectors are orthogonal. That means the set of the column vectors of an orthogonal matrix forms forms an orthogonal basis for the space generated by those vectors. Okay, not only orthogonal. Find out the norm of this each vector. What is the norm of this vector? What is norm? Under root of sum of squares. What is root of sin square plus theta plus cos square theta? 1. What is the norm of this? 1. So
1.
these are the orthogonal vectors whose norm is 1. That means these are all nothing but orthonormal vectors. Each vector of a the vectors of a orthogonal matrix forms an orthonormal basis. Okay, so these two forming an orthonormal basis. These two forming an orthonormal basis for the space generated by u and v. For the space generated by u and v. Okay. Similarly, if you are having so this, they are not just u and v, they are just actually u cap and v cap because their norm is 1. Similarly, if you are having three orthonormal vectors, u1 cap, u2 cap, and u3 cap, that forms an orthogonal matrix because any two vectors are perpendicular and norm of each vector is 1. Therefore, this forms an orthogonal matrix. Is that okay? So, what is this orthogonal matrix? If you are having so how to form this orthogonal matrix? Okay, when you are having a matrix A, let us say for the time being real symmetry. Okay, then you are having three independent vectors x1, x2, x3. These three independent vectors need not be orthogonal. They are just independent. There may be some angle between x1 and x2 other than 90. Okay, so so you identify which two vectors are orthogonal. Let us say for the time's sake, let us say x1 is perpendicular to x2 and which is not perpendicular to x3. Let us say x3 is not at all perpendicular. So you take x1 and x2 which are perpendicular. How do you find the third perpendicular vector? Simplest way is take the cross product of x1 and x2. That is the vector which is perpendicular to the plane containing x1 and x2. Form this as a matrix. That is going to be a matrix. If you divide each vector with its norm, that is going to be an orthogonal matrix. That means this is called normalized model matrix. Previously, if you are forming the matrix P with only x1, x2, x2, x3, which are linearly independent, this is just called a model matrix. This is called just model matrix. This is called normalized model matrix. Okay, model matrix is just a non-singular matrix, but normalized model matrix is an orthogonal matrix. That means P transpose equal to identity matrix in which any two vectors are perpendicular and norm of each vector, magnitude of each vector is going to be 1. Let us say x1, x2, x3 are also x1, x2, x3 where no two vectors are, let us say no two vectors are perpendicular. Then you have Gram-Smith orthogonalization process. Okay, you apply that Gram-Smith orthogonalization process and find out W1, W2, W3, which are orthogonal vectors, and divide each vector with W1, norm of the vector. That is going to be the orthonormal vectors. You put these orthonormal vectors in a matrix form. That is going to be an orthogonal matrix. Okay, this will work for us. Then if you compute P transpose AP, that is going to be diagonal matrix. Okay, or you can say that A equal to P D P transpose. You can say A equal to P D P transpose. Both are one and the same. Okay, so that is how we find out the orthogonal diagonalization of a matrix. Okay, now the question is, this is possible for a matrix, n by n matrix only. For n by n matrix, okay, we have seen a process of decomposing a matrix like P P transpose. But if A is m by n matrix, if it is not at all a square matrix, then there is no question of finding eigenvalues and eigenvectors for A. But we want to decompose this matrix into product of some matrices. Okay. So how to do that? How to decompose a general matrix of order n? That is given by singular value decomposition. That is given by singular value decomposition. So now the stage is set to discuss about singular value decomposition. So can I proceed? Is there any doubt so far?
Yes.
So if a matrix is given, if I ask you to check whether the matrix is orthogonal matrix or not, what you do, you first see the magnitude of each column. If you see magnitude of any column is other than 1, it cannot be a orthogonal matrix. That is not only condition, second condition also you check. After making sure that each column is having unit magnitude, then find the dot product of all the two possible vectors. Every dot product of two vectors must be 0. If you find out any dot product is non-zero, that cannot be orthogonal. So orthogonal matrix has to satisfy two conditions. Any two vectors, any two column vectors are mutually perpendicular, and every column vector is a unit vector. Okay, so that is how we can form the orthogonal matrix. Okay. Now, what is that singular value decomposition? Okay, so I will close this. So what is a singular value decomposition? This one. Singular value decomposition takes a rectangular matrix of order n. It can be any matrix of order n. Okay, it says that this can be always decomposed into u into s into this is u into s into v transpose. What are u and v? U and v are orthogonal matrices. What do you mean by orthogonal matrix? A transpose equal to A transpose A equal to I. That means u transpose u equal to u transpose equal to I. Similarly, v. Both u and v are orthogonal matrices. Okay. So every matrix can be expressed as u s v transpose. Okay. In case of a square matrix, we expressed we may able to express this as p transpose p dt p transpose. In this case, it is going to be u s v transpose. Similar to this, making sense? Where p is orthogonal, and here u and v are orthogonal. And what are the orders of u s v? You see here. Okay. S order is same as A. U order is number of rows. V order is number of columns. And this is V transpose. Okay. Now there is a algorithm which we call it as a procedure in mathematics. Okay. So what is that algorithm? You just see. So you have to know how to find out V. If you know how to find out V, you can find out V transpose. So we are going to see how to find out V, how to find out S, how to find out U. Finally, you show that U S V transpose equal to the matrix A. Okay. So if you complete these four process, that means to say that you have completed you have shown the singular value decomposition of a matrix. Okay. So how do you find out this? So when a matrix A is given, okay, you find out A transpose A and AA transpose. Okay, you find out A transpose A and AA transpose. You just see what are the orders of AA transpose and AA. So if A is a matrix of order m by n, what is A transpose order? N by m. So what is the resultant? It is an n by n matrix. So it's an n by n matrix means it is a square matrix. This square matrix will have n eigenvalues. Okay, those eigenvalues are denoted like this. Okay, so you find out the matrix, you compute the matrix A transpose into A, which is a matrix of order n, which will have n eigenvalues. Arrange those eigenvalues in the decreasing order. Okay, suppose if you are having 6, 7, 2, then arrange them as 6, 7, 6, 2 like this. Okay, so you arrange eigenvalues in the decreasing order. Okay, in this some of the eigenvalues will be 0, some of the remaining eigenvalues is going to be positive. Okay, so A transpose A mean to say it is always semi-positive definite. That means you cannot find out a negative value. So that means you may get eigenvalues like this. Okay, lambda 1 greater than lambda 2 greater than and so on up to r, up to lambda r. These are all non-zero eigenvalues, and from r plus 1 onwards the remaining are all 0. Okay, so note that lambda equal to 0 for I greater than r. So lambda r plus 1, lambda r plus 2 and so on up to lambda n are going to be 0. Lambda 1, lambda 2 and so on, lambda r has to be non-zero. Okay, so find the normalized model matrix V. Okay, find out the normalized model matrix V. That means what? You find out the eigenvectors corresponding to all these eigenvalues. Okay, then using those eigenvectors, okay, you create a normalized, you create a orthonormal basis. You put each vector as a column vector of matrix. That is going to be normalized model matrix that I have shown today here. Okay, where? Okay, if these are the eigenvectors of A transpose into A, from this you create a normalized model matrix like this. Okay, this they are calling as that they are calling as V1, V2, V3. So what is this? When I say this is a normalized model matrix, this is going to be orthogonal matrix. That means any two vectors are perpendicular and each vector magnitude is going to be 1. That means we got already a orthogonal matrix V. Once you have V, you can find out V transpose. And what then you define some elements like this. Sigma I. Sigma I is nothing but positive square root of the eigenvalue. Up to what? Positive square root of the non-zero eigenvalue. Okay, you have n eigenvalues. You collect the non-zero eigenvalues. For each of the non-zero eigenvalues, you take the square root. Okay, the value which is obtained, so-called singular value. This is called lambda I is the positive eigenvalue. Square root of lambda I is the singular value. Okay, so then for each of the singular value, you define a matrix like this: ui equal to 1 by sigma I into A into Vi. What is A? A is an m by n matrix. Okay. What is V? V is an n by 1 matrix. What is the product? Product is U. Something like U or Y or something. What is its order? M by n into n by 1 is, it is m by 1. Okay. U vector is having m components. Divide each of the component with a singular value. Okay. That is going to be the column vectors of U. That is going to be column vectors of U. Like that, how many column vectors you computed? R column vectors you computed. But U contains how many elements? U contains m columns. U contains m columns. What you computed is U1, U2 and so on, UR only. So how many columns are to be filled still? Out of m columns, you got R columns through this formula. So how many columns are left out? M minus R. Do you agree? These m minus R columns, okay, you find out by finding the eigenvalues corresponding to AA transpose. Okay, eigenvalues corresponding to AA transpose. Okay, note that suppose A is a 3 by 4 matrix. Let us say A is a 3 by 4 matrix. Okay, then or you consider A is a 4 by 3 matrix, or you consider A is a 4 by 3 matrix. Then what is A transpose A? This is 4 by 3 and this is 3 by 4 means it is a 3 by 3 matrix. Okay, similarly what is A transpose? Okay, A is 4 by 3, A transpose is 3 by 4, so product is going to be 4 by 4 matrix. And This 3 by 3 matrix will have eigenvalues, 3 eigenvalues. This 4 by 4 matrix will have 4 eigenvalues. And you will notice that eigenvalues are all the non-zero eigenvalues are going to be same. Suppose if it is 4, 5, 6, then eigenvalues of this is going to be 4, 5, 6, and additional eigenvalue is 0. Okay, so corresponding to this eigenvalues, you computed the normalized model matrix. What is it? V1, V2, V3 we computed. Okay, corresponding to these eigenvectors, we computed U1, U2, U3. What are those? 1 by sigma 1 into, what is sigma 1? Root of lambda 1. That means root of 4 is sigma 1. Root of 5 is sigma 2. Root of 6 is sigma 3. So 1 by sigma into U1. 1 by sigma 2 into U2. 1 by sigma 3 into. So this is nothing but what? This is denoting with V. And 1 by sigma 3 into U3. With these are all V1, V2, V3. Okay, so V1, V2, V3. Then you will get U1, U2, U3. But you put them U1, U2, U3 here. But one more column is left out. Okay, that column vector you find out by finding the eigenvectors of 0 corresponding to this vector. Okay, if you don't want to apply this one, then you find out instead of going eigenvectors, instead of finding U1, U2, U3 like that, you find out normalized model matrix corresponding to all these vectors of A transpose. That is going to form U1, U2, U3, U4. Okay, but instead of going like that, you simply go with U1, U2, U3 like this, and U4 only additionally, if at all any unfilled column is there, that unfilled column is going to be the eigenvectors corresponding to 0. So find out the vector corresponding to 0, find out the eigenvector corresponding to 0 of A transpose, which is orthogonal to these three vectors. So that then you can find, so that all the vectors are going to be mutually perpendicular, and you can make these vectors into normal vectors. If at all, if any vector is having non-zero magnitude, then form the normalized model matrix corresponding to A transpose, and that is going to be U. That is going to be U. So once you have U, A and U, what is S? S is nothing but you are having sigma 1, sigma 2. You put them as diagonal elements. Fill up the remaining elements 0. Fill up the remaining elements 0, so that this matrix is going to form an m by n matrix. Okay, so you just put these non-zero square root of the eigenvalues, singular values in a diagonal form. Fill all the elements, remaining elements with 0, so that this is going to form matrix. This is going to form a matrix of order m by n. That's it. So once you have S, U and V, if you observe that, if you compute U, S and V transpose, you will notice that this is nothing but A. Okay, so what are the steps involved? So when a matrix of order, for a matrix of order A, there are three tasks. Okay, one is computing V, other one is computing U, other one is computing S. Okay, V is nothing but a normalized model matrix corresponding to A transpose A. Normalized model matrix corresponding to A transpose A. Okay, and U is nothing but a normalized model matrix corresponding to AA transpose. AA transpose. Okay, and that some part of this U can be obtained through V with the help of the vectors of V. If any remaining vectors are there, that can be obtained through eigenvectors corresponding to lambda equal to 0 of AA transpose. Okay, that can be done. And remaining is forming a matrix, okay, whose elements, diagonal positions are filled with non-zero filled with singular values, which are arranged in decreasing order. Lambda 1 greater than, obviously sigma 1 greater than sigma 2, lambda 1 greater than lambda 2 greater than lambda 3 means obviously sigma 1 greater than sigma 2 greater than sigma 3. And fill up the remaining elements with the zeros so as to form a n by n matrix. Okay, later you show that U S V transpose equal to A, that completes the singular value decomposition. And that will be demonstrated through an example now. I'll show you. Okay. So, is this visible clearly? Are you able to see this? Because I did it manually and took the scanned copy. And there is no single procedure available in the literature. Okay, different authors are explaining different algorithms, giving different algorithms for a singular value decomposition. Whatever the procedure I am explained now will work for any matrix of order n by n. Are you able to see this matrix? Can you read out this? Is this visible to you?
Yes.
So what is the matrix says? Matrix is 1 0 1 0 1 0 0 2 0 1. Okay, you can see this is a matrix of order 3 by 2. It is having 3 rows and 2 columns. Okay, so find out A transpose A first. That is what the algorithm says, right? First you compute A transpose A. What is A transpose A? When this is A transpose is converting rows into columns, columns into rows. So 1 0 0 is written in the first row, 0 2 1 is written in the second row. This is A transpose, this is A. So I multiplied these two matrices, I got a 2 by 2 matrix, which is a diagonal matrix, and I know which is a triangular matrix. I know eigenvalues of a triangular matrix are its diagonal elements. Therefore, I can directly list out what are the eigenvalues. Eigenvalues are 1 and 5. But those 1 and 5 I arranged in a decreasing order. Highest magnitude I took it as lambda 1. Next highest magnitude I took it as lambda 2. So instead of writing 1 and 5, I wrote it as 5 and 1. Then what are the singular values? Here there is no zero eigenvalue. All the eigenvalues are non-zero. So what is my singular value? Square root of 5. My next singular value is square root of 1, which is 1. So when 5 and 1 are eigenvalues, root 5 and 1 are called singular values. Okay. Now you find out the eigenvectors corresponding to A transpose, corresponding to lambda equal to 5. For what matrix? For this matrix. You know how to find out eigenvalues and eigenvector. Because these two are eigenvalues for this matrix, I want to know the eigenvectors corresponding to these two eigenvalues with reference to this matrix. And you know the procedure how to find out eigenvectors corresponding to an eigenvalue. Determinant of solve the system of linear equations. For the time being, you call this as P. Okay, B minus 5y into x equal to 0. This is a homogeneous system. Solve the system and get the solution. Solution is in the form k1 into v1. So this is v1. So first vector is 0 comma 1. Similarly, I find out the eigenvectors corresponding to 1. Again, that means okay, A transpose A minus 1 into I into x equal to 0. You solve this homogeneous system. You will get a solution of this form k2 into 1 comma 0. Okay. Therefore, what is my second vector? K2 V2 means V2 is 1 0. Now what is my matrix V? V is nothing but putting the V vectors as V1 and V2 like this. Okay, first I have to confirm that this is a orthogonal matrix. If it is not an orthogonal matrix, you make this into orthogonal matrix. Use these vectors V1 and V2. They are linearly independent. From linearly independent vectors, you create an orthogonal vectors by using Gram-Schmidt orthogonalization process. Okay, and then you divide each vector with its norm so that you will get an orthonormal basis. You put those orthonormal vectors in the form of a column vectors of V. That is going to be the orthogonal matrix. Clearly, in this case, we don't need to do all those things because 0 comma 1 is a unit vector V1 and V2 is 1 comma 0. This is another unit vector. These two are perpendicular. So therefore these two are perpendicular. Norm of each vector is 1. Therefore each is a unit vector. Therefore this is automatically forming an orthogonal matrix. So my work is done for V. And what is S? S is nothing but matrix whose diagonal positions are filled with singular values, and fill the remaining elements with 0 so that you will get a original matrix order. Original matrix order is 3 by 2, 3 rows and 2 columns. Okay, 3 rows and 2 columns. So you form a matrix of same order as A. So I put sigma 1 sigma 2 here, and you frame a m by n matrix, 3 by 2 matrix, by filling the remaining elements with 0. So S is also formed. So what I require is only U. What is U? U1 is because you are having V1 and V2. Because you are having V1 and V2, you can find out U1 and U2 by using this formula 1 by sigma 1 into AV1. What is sigma 1? Root 5. And A is this matrix. What is V1? First vector of V, 0, 1. Multiply these two matrices, divide with root 5. Then you will get a vector, first component. You can see this is a unit vector. Find out the norm, 0 square plus 4 by 5 plus 1 by 5. 4 by 5 plus 1 by 5 is 5 by 5, which is 1. So this is a unit vector. What is U2? 1 by sigma 2 into AV2. What is sigma 2? Sigma 2 is 1. A is a matrix. V2 is the second vector. V2 is the second vector of V. That is 1, 0. Okay. So A multiply with 1, 0 and divide with 1, you are getting this vector. So you can see this is also a unit vector. And notice that these two are perpendicular vectors. U1 is perpendicular to U2. You can see. So 0 into 1, 0. 2 by root 5 into 0 is 0. 1 by root 5 into 0 is 0. These two are perpendicular. So you got U1, U2. Already you got U1, U2. What you want is U3. As I told in the previous case, you can find out U3 by taking the cross product of U1 and U2 and divide with its norm. Okay. Other way is you find out the eigenvector corresponding to lambda equal to 0 of this matrix. What is AA transpose? AA transpose is A is this, A transpose is here. This is a 3 by 3 matrix. If you find out the eigenvalues, you will notice that the eigenvalues are 5, 1, 0, which are same as non-zero eigenvalues of this. Non-zero eigenvalues of this is 5, 1. So as I said earlier, A transpose A and AA transpose will have the same non-zero eigenvalues. So this is 5 by 1. Additionally, 0 is there. Now you find out the eigenvector corresponding to lambda equal to 0. Okay. Then so that is what I did here. So eigenvectors corresponding to lambda equal to 0 of AA transpose. Okay. AA transpose minus 0 into Ix equal to 0. So when you solve the system of linear equations, homogeneous system, you will get a solution for X. Okay. You will get a solution. You will get infinitely many solutions. You say I said between two linearly independent vectors, you can find out several vectors normal to this vector, because any multiple of cross product is also a vector perpendicular to the plane containing these two. Okay. So I took k3 equal to 1. You will get a simplest vector 0, 0, 1, minus 2. Okay. So this is U3, but this is not our candidate, because our candidate should have norm 1. So you normalize this. Okay. This will be perpendicular to U1 and U2. This is U3, but U3 does not work. I'm calling this as U3 dash for the time being. Okay, because the previous one are U1 and U2. You need to normalize, because I want only unit vector, not just vector. So what is its magnitude? Root of 0 square plus 1 square plus minus 2 whole square is 5. So divide this vector with its norm, so that this we can say a unit vector. So you call this as U3. U3 is nothing but U3 dash by norm U3 dash. Okay. So you find out U3 like this, or what I am telling, the other technique is, if you are having only 3 components, the other technique is you find out U3 dash as a cross product of U1 and U2 and divide U3 dash with its normal. Then substitute that U3 dash here, you will get U3. Okay. So simply taking the cross product and dividing with its norm work, or you finding the eigenvector corresponding to lambda equal to 0 of AA transpose also will work. Both will be fine. Okay. Then you put those 3 vectors. Okay. So this is the vector 1 by sigma 1 into AV1, which is U1. This is another vector 1 by sigma 2 into AV2, which is U2. So U1 and U2 already obtained, and U3 we just now obtained. You put them as 3 vectors, and you observe that any 2 vectors are mutually perpendicular, because the dot product is 0. These 2 dot product is 0. These 2 dot product is 0. So any 2 vectors are mutually perpendicular. So therefore these 3 forms an orthogonal basis. And in fact, they are orthonormal. They forms an orthonormal basis. Why? Because magnitude of each vector is 0. Am I recording this? Okay. So therefore, the matrix so formed is going to be an orthogonal matrix. So U is an orthogonal matrix, V is an orthogonal matrix. Now we computed S. If you find out USV transpose, you will observe that this is nothing but the Where is this? You will observe that. Okay, so product of these two matrices is turning out to be this. This matrix multiplied with this matrix is turning out to be this, and this is nothing but A. So we found two orthogonal matrices U and V such that A can be decomposed as U into S into V transpose, where U and V are orthogonal matrices. Okay, so this procedure works for any matrix. Okay, is it clear to all of you how we found singular value decomposition? Okay, so that ends the concept of singular value decomposition.